Jai Hind. My name is Vivek Agarwal. I am the assistant professor in the Department of Computer Science and Engineering in AKGEC. So today we are going to discuss with a very interesting topic, that is SVM, support vector machines. And this is a technique which comes under the supervised learning. That is a kind of the learning of various kind of the learning types of machine learning. And specifically, if I talk about the SVMs, they can be used for the classification problem mainly, but can be used for the regression problem as well. And if I talk about the data types, they can, or I must say, the data set on which they are most comfortable. These are the linear. By default, the acceptance of the data is linearly separable data, but they can work on the non-linear data as well. So we are going to deep dive in the topic, and we'll discuss the essential properties and the things about the SVM. If I need to introduce about the SVM, it is the widely used, the most commonly used approach for the general purpose applications of the machine learning. So very interesting topic. Let's come together. So if we talk about the SVMs, the full form is the support vector machine. So it works on the concept of support vectors. Like you can see, this is behaving as a support vector. This another data point is also behaving as a support vector. So how it is works? First of all, the whole data set we are having with us for the past experience, I must say that for the training purpose of the machine learning model. So I need to plot that data set into the I must say that dimensional plane. I must say the high dimensional plane. The dimension of this feature space can be distinguished or can be assigned as per the number of features. Suppose your data set is having the n number of input features, then there must be n dimension. There could be n dimension of that data in the feature space. So for example, we are having the two input features. Then these features can be plotted using a 2D space, 2D features space. So we are having an assumption, like we are having a data set which is of having two input features, and the problem is of the classification. All these points are classified as the class A, and all these points are the classified as class B. So we can plot all the data points available in the data set using a 2D plane, which can be called as like X plane and the Y plane. So after the plotting these points, these are the blue color points which are belonging to the class A, and these the green dots are belonging to the class B. So we need to separate them using an hyperplane. The algorithm is based on the hyperplane concept. We need to distinguish them using a hyperplane. So this is your hyperplane. If we talk about the hyperplanes, there could be several hyperplanes. If you see, like there are these points are plotted on the X plane and the Y plane using a 2D plane. Then these are the points, they can be distinguished, or I must say there can be various lines, various separating line can be drawn between them. This could be like this could be like this, and other one could be like this, one could be like this. So there could be various lines, possible various lines. Now the question is, which line must be selected as the hyperplane, or I must say the decision plane. So what is again, it will segregate the n-dimensional space into the classes. Already we had talked about new data point into the correct. Now how the concept works, when we have this optimal hyperplane, we need to make it a broader, like it is not a line, it is like a plane. So for making a plane, we will have to add some width to the hyperplane. So for providing that width, we need to maximize this distance between the two classes. So for that, we use the concept of this margin. These margins, this is the margin towards the class A, this is the margin, this one, this is the margin towards class A, and this is the margin towards the class B. Collectively, this is a maximum margin which can be between the class A and the B, the collective margin, the total margin. So the choice of the plane, as I discussed here, like multiple lines can be drawn, multiple planes can be drawn between the two classes, but which one to be chosen, that is decided on the basis of this margin. The whole idea is to get this maximize. The margin should be the maximum. So we need to identify a hyperplane which is having a maximum margin. So we can choose that plane as an optimal hyperplane for our problem. So this is the whole idea. Now how it works, whenever now we had just plotted the hyperplane, we have designated the margins, and now when the new query point or the real time data point comes into the feature space, we need to allocate that particular point, is belonging to the class A or can be belong to the class B. So that is being decided on the basis of its position, the position of the point. Suppose the point is plotted here, so that is clearly would be assigned to the class A. If the point is plotted here, then clearly that would be plotted to the class B. Suppose if the point is here, again that would be plotted to the class B. If the point lies here, then again it would be separated to the can be classified into class A. But if the point is lies somewhere here, then there are some other techniques through which we can decide actually to which class we can assign it. For that we use a C parameter. So already I have told you this is one of the very popular and widely used supervised machine learning algorithm, primarily used for the classification problem, but can be applied for the regression problem too. This is robust for the robust against the overfitting, because most of the machine learning models goes under the problem with the overfitting, but it can cater these overfitting issues. And this works very well with the high dimensional data set. High dimensional data set means the number of input features. There are various machine learning technique algorithms and the models. They got confused. They got lost their performance in the case of high dimensional data set, means when the number of input features are in a good quantity. But the SVM is quite comfortable to handle with the high number of input features, or I must say the high dimensional data set. That's why it is very popular among the designers, ML model designers. It can be utilized for the image classification as well, text classification, and the bioinformatics. SVM is not a good choice for the big data problem, as it might not scale well with the large data. Yes, this works very well with the mid-side or the I must say the small size data set. But in the case of when the number of data points, or I must say the data inputs, data rows are quite in a large number, then this model could be failed, just because the reason behind that is, you can see when you are having a high dimensional space and you are having a maximum number of or I must say in a huge number of input data input points, then there would be a very tough call to find a straight line, to find a hyperplane between these points, because they would be highly I must say the mix to each other. They would be having the high proximity, having the different class, but they are lying very closely to each other. So there, it is very tough. In that case, it would be very tough to identify a proper hyperplane between the multiple classes. So that's the reason about this, the last point. So come further. Yeah. So the SVM algorithm has already we had an idea about this help best line or the decision boundary. The best boundary or the region is called as the hyperplane. This is called the hyperplane. And SVM algorithm find the closest point of the lines from the both classes. Already I have given you some idea, and the choice of these lines is based on these support vectors. Yes. So these close points are called as the support vectors. The distance between the vector and the hyperplane is called margin, and the goal of the SVM to maximize this margin. The hyperplane with the maximum margin is called the optimal hyperplane. Already I just discussed a little while before. So the point is, let me have a big picture. So the point is, whenever we are having a data set, we just plotted the data points into a multidimensional or the feature space. Suppose we are having the two input features, so we plotted this x and y. Suppose we are utilizing the 2D space because we are having the two input features, and we just plotted the whole data points in this feature space. Now we find out this, we through some mathematical calculations, through some geometrical calculation, we just got this hyperplane, the optimal hyperplane. Now the point is to decide these support vectors. Whenever starting from this hyperplane, when we are moving towards the class B, suppose this is class B and this is the class A data points. Whenever we are moving towards the class B, the parallel to this hyperplane, the very first point which is connecting, which is interacting or intersecting with that imaginary line, that could be considered as a support vector of the class B. It could be a single point or it could be the multiple points as well. So collectively these multiple points could be called as the support vectors towards the class B. Likewise, when we are moving towards the class A and having some parallel imaginary lines, so the very first point or the multiple points which are being intersecting with that imaginary line could be called the support vector towards the class A. So there could be minimum 2 support vector for any SVM machine, or there could SVM, or there could be many more than 2 as well support vectors. So why we call them the support vector? Because we know very well, if we are talking about any data point, suppose D1, it would be having multiple values. That's why it is called the vector. Vector and the direction as well. Whenever we talk about the vector, it is having the two things. It is containing some magnitude and the direction. So here the direction part is something for the classification, like to which class it is being lied, or the exact position, or the, I must say, the side of the optimal hyperplane. So for that purpose, we called this the vector. Okay, we talk about the data on which the SVM can be applied. It could be the linearly separable data set. Means the whole data set can be linearly separated. Means if there are 2 or more than 2 classes, they can be separated in the feature space using a straight line. So kind of the problem comes under the linearly separable problem. For that we can utilize the linear SVM things. And when the data is not linearly separable, means when we are not able to classify the classes using a straight line, like the data points are not being able to classify using a straight line in a feature space, then kind of the problem comes under the non-linear. If we are handling these kind of the data set or kind of the problem using the SVM, the problem is called as the non-linear SVM. So how to deal with these things? Let's see. So let's understand the non-linear issue. Already I told you, if there are the 2 class data points, suppose this is for the class A, the blue points, and the green circles are belonging to the class B. So if you see, we had plotted all these points into a 2-dimensional space, X and Y. Now, if you see, we are unable to draw a straight line which could separate all the data points into separate classes. Like if I draw a line here, these points are also connected here. If I draw something like this, then again the points are still mixed with each other. So what is the solution? The point is, what is the solution? If it is a problem of linearly separable, means they must be divided through a linear line, a straight line. They must be divided separately into the 2 different classes. But it is a typical example of the non-linear, means the data is not linearly separable. So how to deal with it in the case of SVM? So for that we have a trick. So let's understand. The original feature space is the space defined by the input features of the data. Each dimension is the space. Already we had told, like if there are the 2 features like height and weight, then we can have the 2 dimension X and Y. The primary goal of the SVM to find the hyperplane that best separates different classes of data point. Yes, we need to find out the hyperplane means a straight line, kind of the straight line we need to identify. But however, in many real world scenario, the data is not linearly separable in the original feature space. Then we need to apply some trick called as the kernel. So it is very important thing or important point in the case of SVM. SVMs are incomplete if we are not talking about the SVM kernels. So what SVM do? Let's understand. So this is your 2D data, two-dimensional data. Now we just converted it into a 3-dimension. Like this is your XY and we just added a new dimension as a Z. Suppose like this. We added a Z dimension and now we are seeing the data. Like if you consider a room, there are some points which are, if you are seeing from the top view in a room, if you are seeing the data on from the top, in the top view, you are seeing the data points in this manner. But if you will see the same data points from a corner of the room, from a corner to the room, then you can see the data something like this. Means a class which is separated outwards, but it is somewhere have some height in a plane, or I must say that in feature space, and one class data points are totally to the downside. So converting this low dimensional data into high dimensional data, until we need to make it a conversion to a higher dimension, until we are not able to find a such scenario where we can easily separate the different classes into different region using a plane. So we are going to apply the, I must say, the high dimensional conversion. We need to convert the low dimensional data into high dimensional data again and again until we are not able to find a such reason or a such condition where we can separate these two lines separately using a straight line or the straight plane. So I think this would be quite very clear to you now how the kernels are working. So we can understand it like this. So we just plot the hyperplane using the, which can be demonstrated using a straight line. But if you see the same thing into a 2D, that would be seeing, that can be seen like this. Like in a room, you just draw a hyperplane in the mid of the room. Suppose like this, you just plotted a hyperplane. But if you see from the top, you will see that plane into something like this. So using this picture, it would be more convenient to you to understand. Suppose this was the data which was classified, which is being seen in the 2D, but we converted into another dimension, a higher dimension like 3D, and we just got after the 3D conversion, we just got the picture like this. All the blue points, these blue points are belonging to the class A, and these red points belonging to the class B. So all the blue points or the class A points are having a position in the Z plane, and all the class B points are having the another position in the Z plane, which can be easily separated using a plane. Because we are seeing it in a 3D, so we can call it, a simple line can also be called as a plane. So now you can understand. So how we did it? We did it using a kernel. So what is kernel? Let us understand. So it is a mathematical function that help organize the data and make it easier to classify. SVM algorithm use the mathematical function defined as the kernel. So what is kernel? Is a mathematical function. Yes, what is it? It is a mathematical function used to take the data as input and transform it into a higher dimension. Means a data point which is having, suppose, x and y dimension, x and y point only, a data point which is having x value and the y plane value, we just converted into a 3D, suppose x value, y value, and added a new point or the new value in the data point, that is z plane value. So this conversion is being done mathematically. One more point I need to add, this SVM is pure geometrical model, a geometrical machine learning technique That's why mathematic make it more robust again the things, because there is no fuzzy logic, there is no fuzzy I must say the interpretations are there. It totally based on the mathematics. So in other words, the kernel function converts the training data to non-linear to the linear equation using the higher dimensional space. Different. If we talk about the is there any a single kernel which is capable to deal with all kind of the non-linearity? No, there could be several kind of the non-linearity, and to handle such non-linearity, we must be having a different kernels, or I must say the different mathematical functions which can be utilized for making a lower dimensional data into the high dimensional data, or the non-linear data into the linear data. The some few popular SVM kernels are the linear kernel and the polynomial kernel, and RBF radial basis function, or the Gaussian. Both are similar, but having a special Gaussian is a special case of the RBF. So RBF could be there, RBF kernel, the Gaussian kernel could be there, sigmoid kernel could be there, and we have a special kind of the kernel called as the customized kernel, where you can customize the kernel as per your requirement. So how it is working? This is linearly separable data. Then we can apply a simple linear kernel. But if we are having the non-linearity in our data set and the data points, then we will have to apply the any non-linear kernel. That could be RBF, that could be Gaussian, that could be sigmoid, that could be any customized, or that could be non-linear, right? So we can see the another example. We can understand the operation of kernel in the SVM machine using this example. So if your data points are classified or the plotted in the two-dimensional space like this, we can convert using the apply the kernel. We need to make it in a position. We need to make it up to a higher dimension. We need to convert it into higher dimension until we are not able to have a such scenario where we can separate these two different classes data point using a plane, using a surface. So this surface is called as the decision surface, or we can call it a hyperplane. After just classifying or after just identifying this hyperplane, we need to find out the margins. So starting from this, whenever we are having our point which can be touched through an imaginary parallel line of this and this, where we are having, in this case we are having more than one point which are connecting, which are intersecting with this imaginary line parallel to this plane. So this is your margin for the class A, and this is the margin for the class B, and completely this is your maximum margin between the two classes. So common kernel functions can be described like this. The function for the linear, mathematical function for the linear kernel is like this. For the polynomial, the function is like this. For the Gaussian and the RBF is like this. For the sigmoid is this. And if we are using any customized kernel, then that could be derived as per your calculations. So now again the challenge is which kernel must be chosen. Like we are having a data set, we are having a problem, and we are solving it through a SVM. Now we just got an idea, like my data set is not being able to be separated using a linear way, means the data set is not a linearly separable data. We are not able to classify using a straight line using a normal kernel or the linear kernel. Then which non-linear kernel must be chosen? Like if we are having the non-linear kernel, we are having the sigmoid kernel, we are having the RBF, we are having the Gaussian kernel, which must be chosen, right? So that must be decided using various factors could be there for the choice. Mainly factor used to be the kind of the application for which you are going to use that SVM trick or to solve that problem. Another criteria could be the kind of the data set, what kind of the data your data set is containing. These are the two factors on which you can decide which kernel must be chosen. And there are the two things, whenever you are not having a good idea about the input features, about the data type of the data set, or you're not having a good idea of the like which kernel must be chosen. Again, after analyzing the data type and your problem as well, you are not able to find out the which kernel must be chosen. Then we are having a solution for that as well. So let's understand. So linear kernel is the common, or the, I must say, the by default kernel used by the SVM. It is good for the text classification. Means if your problem is of your text classification, I must say the document classification, you can use directly linear kernel. As well as it is a by default kernel used by the SVM. So if you are not using any specific kernel, by default it is being used by your SVM machine. Another could be the polynomial kernel. In the case of polynomial kernel, we can have a kernel like this. In the linear kernel, we are having the separation, the decision plane is like this straight line. But in the case of polynomial kernel, we can have a polynomial of any shape. Yes. This is good for the computer vision and the image recognition task. If your problem is of related to any computer vision, or your task is to recognize the image or the image classification, then the polynomial kernel can be used. Third is RBF. Again, as I was discussing, if you are not having a clear cut idea, you are not able to find out the relationship between the data points, if you are not able to find out which kernel must be good for your problem, if you are not having a clear cut idea about the non-linearity of your data, then you can use the RBF and the Gaussian. RBF and the Gaussian are the same thing, almost same, because the Gaussian is the special case of the RBL. It is written as well. The Gaussian kernel is special case of the RBF. So in the case, whenever you are not having a good idea, you can use the RBF. Or I must say that this is the default kernel used by the SVM in the case of non-linearity in the input data set. And then it is a sigmoid. It is used whenever you are having any neural network application. For that, sigmoid could be used. So these are some points through which you can have an idea which kind of the kernel or which kernel must be chosen as per your data type or the data sets data type, as well as your application for which you are using this. Okay. If I need to summarize the whole things about the SVM, although there are a lot of things to discuss about the SVM, but we can conclude the whole points which we already had discussed from starting. So these are the main points of the SVM. First is your margin maximization. Already we had a detailed discussion on this. Means if we need to find out a hyperplane, and after that we need there could be multiple hyperplane between the two classes. There could be multiple hyperplane, but which one must be chosen? We must choose a hyperplane which is creating or which is having the maximum margin between the two classes. So we must choose a hyperplane in keeping this as in mind. We need to maximize that margin. Again, the point is linear and non-linear classification. Yes, by default, the problems to which the SVM is suitable is the linear classification, where the data can be classified using a linear line, or I must say that when the data is linearly separable, we can directly apply the SVM. But for the non-linear classification as well, we can use the SVM as well. For that, we need to use some kernel function. Third is support vector. Very important point for the SVM. Without discussing the support vector or without considering the support vectors, the imagination or the application of the SVM is incomplete, totally incomplete, because the whole idea is belong on the SVM, because the full form of the SVM is also containing the support vector machine. So the whole idea is based on the support vector. Binary and multi-class classification. Yes, by default, this is good for the binary classification. It means where we need to just distinguish the two classes, like class A, like the scenario is like this. We need to separate the data points into two classes, A and B. This is called as the binary classification. But this is not limited to the binary classification. If your data set is having more than two classes, like class A, class B, class C, class D, then also that These scenarios can also be tackled by the SVM using some additional tricks. Okay, robust in the high dimension, already we discussed it in the introduction part. If your data set is having a good number of input features, doesn't matter, it can handle very easily. It can handle such high dimensional data as well. It can work in a good sense. Now the kernel trick, already we discussed, there are various kernel available with the SVM machines or the SVM technique. We can choose as per our data, input data, and as per our application of like the problem we are going to solve using this machine learning technique. So we can choose any kernel out of various kernels available with us. The last point is computationally intensive. Computationally intensive means if we are having a large data set where the data set is having a good number of data points or the data rows, then or the good number of images are there, if we are dealing with the images, then we need to save all that data, as well as we need to save a kernel matrix, because we will have to apply the kernel matrix to whole data for conversion, for converting these data point from lower dimension to higher dimension. And we can make this calculation not only single time, we will have to we can or we can use that calculation multiple times. So for that storing that huge amount of data, we need some memory, computational memory we need. So in that case, we can say the computational cost or the computational complexity is high of SVM only in the case of when we are having a greater data set. Okay, so as a sum up, SVM is effective for both linear and non-linear classification tasks. It works well in the high dimensional space, but it can be computationally demanding. So this is the summary of this. If we talk about the advantages, yes, effective in the high dimensional space, robust for the overfitting, works well with the non-linear data, versatile, yes, can be used for the classification, regression, as well as for outlier detection in the data set. Effective with the small to medium sized data sets, yes, again, if your data set is very high, we can have the problem of finding the optimal hyperplane. That's why this is effective, very effective with the small and the medium data set. But that is limitation of this model, right? It cannot work good with the large data set or the huge data set. Memory efficient, yes, if your data set is not too big, then memory efficient. Good performance on real world problems, that's why widely accepted and widely chosen for the small for the journal purpose applications. Clear geometrical interpretation, totally mathematical interpretations are there, so it is good for understanding as well as for good for presentation and for making the model. If we talk about the issues, the first issue could be the choice of kernel. Many times the designer could be confused which kernel must be chosen. Like already we have several type of the kernels which can be chosen, but which kernel exactly must be chosen? So this may be a case when the designer is confused which kernel must be chosen for a particular problem. So this is a issue which can be handled having a great sense of understanding about the data, and after analyzing the data we can have an idea. Another could be we can use the default. There are various default kernels which can be used in case of any ambiguity or in case of any confusion. So we can use the tricks for solving this issue. Next is model complexity and overfitting. Um, overfit overfit issue arises only when there are the high number of input features. Only then we can have the overfitting issue. Otherwise, SVM deals very effectively in the on the overfitting issue. Okay, the third is scalability. Scalability means scalable when we are scaling our data size or the data set, it must be able to perform well. So this is the issue. Already we know it work well with the small and the medium sized data set, but for the large data set, it has some issues. So we can say this is an issue of scalability. We cannot scale the model or the data set in a the model or the trick for a scalable data sets. We can work only the mid-sized or the small sized data set. Sensitivity to noise data. Yes, if your data is noisy, if it is having mislabeled on any data, or the data type is something different, or I must say if any outlier is there, and if the if the data is not I must say the cleaned, then it may lost its performance. Yes, so it is sensitive to the noisy data because everything is based on the plotting of the data points. If that data is not having appropriate data, means data plotting would be affected, and just because of that points which are available in the dimension feature dimensions, it could affect the finding the optimal plane. So this is the issue: sensitivity to the sensitivity to the noisy data. Choice of hyperparameters. Yes, whenever we are implementing the SVM machine into any through any programming languages, then we are having a function of SVM, and which is having various parameters through which we can hyper tune the model. So in the case of SVM, there are a number of hyperparameters, and which can be tuned for getting the higher performance or the maximum performance. But what value would be the good for having that parameter for having the good performance? So generally, it used to be a issue with the SVM machine to get or to choose the value of that appropriate parameter. Imbalanced data. Like if you are having a data set which is having two classes, and the total there are 1000 entries, and if class A is having 800 entries and class B is of only 200 entries, then this is the case of imbalance. Means your data set is biased, or your data set is having more focused on the class A data type but not on class B data type. So if you are going to prepare a model using this data set which is having the high proportion of a class or particular class, then your outcome model would be maybe biased towards the class A, because it is going to be trained over the maximum points of A, or I must say the presentation in the high dimensional space. Most of the points are belonging to the class A and very few to the class B. If any new point arises, there are the maximum chances that would be classified into the class A. That's why it is the problem which can be handled by balancing this. There are various tricks and various techniques available for balancing your input data set. One of them is like SMOTE function is there. You can use this function to balance your data. Right. Next is your memory uses. Yes, again, if your data set is high for applying the, and your data is non-linearly separable, non-linear type data, then we need a high number of memory requirements for storing the kernel matrix as well as the input data for making them conversion from low dimension to high dimension. So that's why it is a issue with the memory issue with the SVM memory uses. And the last is how to choose proper margin in the high dimension. If you whenever you are having the maximum number or the good number of input features, then sometimes it could be very tough to exactly identify or exactly defining the margins, the maximum margin. So this is again an issue which can be handled using some tricks. There are some mathematical formulas using that we can identify the exact proper margin for high dimensional case. So this was all about the SVMs. We started with the introduction part and how the model is working, how the concept is working, and how for how type of the problems we can apply the SVM, and what kind are the different type of the kernels available in the SVM, and and at the conclusion part we just discuss the main properties, the advantage and the issues with the SVM. So thank you for today. In next lecture we would be having some another topic. Thank you.